NTU World of Wisdom. Welcome to High Impact Thesis. In this podcast, we speak with researchers from various scientific fields to talk about the motivation, goal, and potential impact of their research. We also want to give you a sense of how a PhD is carried out with an emphasis on the PH, the philosophical aspects involved in pursuing a PhD.
All right, everyone. Welcome back to the High Impact Thesis podcast. I'm here with my co-host, Ahmed, and we are joined today by Hasnain. Thank you for joining us.
Thanks a lot.
So why don't we start off with a very general overview of your research topic, just for everyone listening.
Right. So I've grown in Rajasthan. It's a desert state in India. In general, in India, resources are scarce. Not everyone has equal access to the resources, but more in Rajasthan, so that we don't have enough rainfall. And so I remember in summers, water would be supplied at our homes, in 4 days once or in 2 days once. And this would vary, depending on the part of the year. Sometimes it's summers and you don't have rainfall at all, so they lack water supply, so they limit that. And so I remember that right from a very young age, I really like this idea of making decisions optimally. So when you have limited resources, how do you make best use of it? Unlike a resource-rich country like Singapore, where you have a lot of everything, water, and you can ask pretty much everything and you have it. You can use that water for gardening. You can use that water for many other purposes. But where we come from, water is it comes at a premium, and so you really have to put it to good use. So I remember from that point in time, I was very interested and intrigued by this idea of making decisions. Earlier, it was like how humans make decisions, how do they arrive at some decisions, but later it became how do you make good decisions. And then when I was going through my school, through my college, I was a mechanical engineering major, by the way. Right in the middle, I think I took one course on mathematical modeling, and I was exposed to this idea of optimization. I did not know that this formally there's a formalism around this idea of decision making, which is called optimization. Which is a standard problem is that you have some resources and you have some objectives, and you have some constraints. So how do you make use of those resources to maximize an objective? And I really like that idea because it basically connected with the idea of decision making. You have to make some decisions. How do you make them optimally? So yeah, very generic. And then of course, when I grew up, I further realized that you don't have infinite time to make decisions. You have to make decisions sometimes very quickly, and most of the times under uncertainty. You don't know everything. You never have perfect information about the world that you're in. Things are very probabilistic. So this love for basically decision making under uncertainty, I believe now I can look back and really connect the dots. But back then I had no idea that this is where I was going towards. But I had this inherent love for that. So when I was working for a construction company, we had to deploy again some resources. You don't have infinite money. You have human resources are limited. Money is limited. Another question is how do you achieve your targets with the same set of resources that you have optimally, without causing them a lot of headache. You have to also consider about their goodwill and about their lives and stuff. So, and I understood that how powerful this was. Like the guy who was running the company, the project directors, the project managers, they were making these decisions. So bad decisions could impact so many people down the line. Yeah, I think again this theme recurrently came to me back then as well, that you need to make decisions, intelligent decisions. You work always under uncertainties. So and then I realized that at a later point in time that there's a whole branch which goes by different names in different areas. It's called operations research, it's called operations management, it's called decision making uncertainty. Under different colleges, different departments teaches, civil engineering departments teaches, the mechanical engineering departments teaches, computer science departments teaches. So when I got exposed to these ideas in my masters, that was when I was like, no, this is something that I like more than any other thing. And one thing led to the other, and eventually I ended up doing a PhD, which is also the content and in the stuff that I did in my PhD also falls under the broad umbrella of decision making under uncertainty, under the umbrella of operations research.
Mm-hmm. And what was your PhD about?
So I in my PhD at NTU, I worked with Singapore Changi Airport data, and the objective was to make the airport operations safe and efficient, and also passenger sensitive. So at an airport, you have two regions. You can divide an airport into two subsystems. One is what we call land side, and another what we call air side. So land side is that portion or that part of the airport where we as passengers go, where we have those lounges, where we relax, where we have those duty-free shops where we buy stuff from, we buy tickets from, where we get queues and all of that. That's called land side. The other side is called the air side. The air side is the part where aircrafts land, they take off, they taxi, they are parked at the gate. So in my research, I tried to again optimize operations at land side and also operations at land side, and try to do that in a way that they work synergistically and not the other way. When you improve some work somewhere, because it's a complex system, efficiency somewhere can translate to inefficiencies at other place. So then you don't want to end up in that situation. So a large chunk of my PhD is about improving airside operations, improving aircraft movements, basically orchestrating aircraft movements so that you have less delays. And I say to make it efficient and safe, I mean by efficiency we mean less delays. And by safe we mean that aircraft should not come too close to one another, so that there's no case of runway incursion or runway excursion wherein people's safety is at risk, and aircraft there's a lot of money involved even in the aircraft. If it gets into accidents with in any obstacle or with other aircraft, that's a disaster. So you want to schedule operations, manage operations such that basically control things so that you don't end up in a bad situation. So specifically, my PhD was about reducing the delays at the taxiways, at the runways, and do them in such a way that passengers don't get affected. They are still able to make their connections. So that was what I did specifically in my PhD.
So is the runway considered part of the airspace?
So as I said, there's something called airside.
Airside, sorry.
Yeah. Airspace is like the en route where aircraft fly. My research is all about ground movements of the aircraft. So airside is basically taxiways and runways. But a large part of my research didn't have to do anything with runway. I take that as a given. So every runway has a schedule. Now again, this idea of optimization really comes is when you have runways and taxiways are scarce resource. Every aircraft that comes in an airport has to be serviced at a runway, and when it takes off, it has to use that runway. And so you can only serve as many aircraft as you can basically service at the runways. Similarly, when you have the taxiways, Changi Airport has only few runways. They're making another terminal which would be operational, I believe, by quite late. I mean, it might take 10 to 15 more years when it's fully operational. But that's something in the future. Right now, Changi and Singapore, it's of strategic importance to them that Changi is able to cater to different passengers from all over the world. So Changi is like a hub. There are different models in which airports operate. One is what you call hub and spoke model. So different flights feed into Changi, and then from Changi, these passengers which have come in different flights fly to another destination, let's say Australia or US. So there's a long haul flight. Again, there are different models in which airports operate. Changi Airport is essentially a hub and spoke model wherein it attracts all the flights from different areas, and then all the passengers come here and then they go to another destination together in a long haul flight. So it's of importance to Changi that not only that airside operations are efficient, but also that passengers don't miss their connections, because that's a very terrible situation for any passengers to be in. That once you can get delayed, but if you miss a connection, there's a lot of problem, not just for you, but even for the airlines, if it is their responsibility to connect you to another flight, or basically found accommodation for you. But then equally important for them is how long can they make their flight wait. Because, for example, if let's say your flight was delayed because of any reason, because of some other airports or because of this current Changi Airport operations that that make that flight wait at the tarmac and it's not able to be parked, the problem is that for you, the aircraft cannot wait indefinitely. It has to fly its next leg. Otherwise, the passengers on this aircraft will be late for their destination. And so then it is a cascading effect. Again, you have limited resources, limited time, and you don't know what will happen in the future. If you choose to wait this flight, how much more time would this next aircraft is going to connect will take? So you never have perfect information, so you always work with probabilities. Yeah, to answer that specific question, it is more. So my research was more about, although airside do contain this runways, but I was more focused on the gates when passengers go, and I mean they come and they basically transfer to another gates, take their boarding flights, and then take off flight, and they take off from this Changi airport. But the research is very general. Like if it can be applied to Changi, it can be applied to any other airport. So my focus was on gates and on taxiways. When do you ask the aircraft to start? So specifically, there's the problem that I really worked for a lot of time in my research was about departure metering. It's called airport departure metering. So metering is the concept of basically controlling the start times of the aircraft, so that they can reach their destination. So in my case, I'm controlling the start times of the departing aircraft. So we call that in our domain pushback time, the time when the aircraft will be pushed back from the gate. You control the start time or the pushback time with two objectives. First objective is the runway, as I told, is a scarce resource. You don't want to starve it. So there should always be some utilization of the runway. So you don't want to starve it. You want to constantly feed it with the aircraft. Yet at the same time, so one way to achieve this is that you just put every aircraft that is ready and ask it to go and depart. And what you end up having is a long queue of aircraft. You have a good runway pressure, but you have a long queue of aircraft waiting for their runway slot. So what then happens is that these aircraft are idling, they're burning fuel. Passengers are having a difficult time just being on the tarmac, things are not moving. So it basically diminishes their experience, and then it's just waste of fuel. So now the question is, how can I, as I said, I keep telling, orchestrate the times, the start times, we call that departure metering, so that both these objectives are met. The two objectives, again in a very specific term, is runway utilization. The runway you should be able to utilize it to the best of your capabilities as an airport. But at the same time, you want taxiway delays to be very less. So then the idea is that can you release them in time just so that they reach the runway just in time, and yet they don't have a lot of traffic to contend with. They can just find their ways very easily. So now to think about how can I release each aircraft from their gates, and there are like many gates at Changi, so that when they come to the runway, they find their runway available, and yet they have not stopped and go. And there's a very common phenomenon, stop and goes. When we're driving in real life, in cars and in motorcycles and cycles on roads, there are street lights, right? And they make a stop. But on airport, you don't have that. So what ends up happening is the pilot sees the next aircraft ahead of it and sees that it has stopped, so it has to also stop. And then it leads to queue formation. So you really don't want to end up there as well. You need to find a sweet spot.
So just so I make sure I understand this correct, the ideal situation would be for me as a pilot to get the go from the control tower, run my engine, and then just keep going on the taxi and then on the runway and take off without stopping.
Exactly.
And that should happen to all the airplanes.
Exactly. Can you do that at a global scale? Can you do it at the airport level, not just for flights?
So this sounds very similar to manufacturing.
Yes.
Like a manufacturing line,
Yes.
like and all the theory behind it, like sending parts in at the right time where they get used and then they get, pushed on to another line.
I incidentally use that word just in time, which is actually we borrowed from mechanical engineering, wherein this concept, and I think people working in mechanical engineering, industrial engineering are very familiar with. You just want to produce enough so that you don't end up with a lot of inventory, because inventory keeping cost is also a lot. You need space, you need to just make enough so that it reaches market. And this can really make or break a company, by the way. It's not just making good stuff, but it's also about, this is what we call operations research. You want to optimize the operations so that you can maximize the productivity and the profits. So yes, a lot of ideas in this area are borrowed from control theory in electrical engineering, are borrowed from just in time and things like and operational concepts like these in mechanical engineering. So it borrows from multiple areas. It's quite interdisciplinary in that sense that you have to use, and a lot of those ideas really help. So the algorithms that were developed before, I think this is a problem that has been studied for the last 2 decades. The first paper in that field. We could call that a pioneering paper, which basically gives us idea of a virtual queuing. So what does it mean? That basically means that instead of having a physical queue, you can have a virtual queue. So you can assign that pilot his slot. So let's say there are 10 slots, 10 aircraft want to go to the runway. You give each one of them their queue number. And then when a particular... But back then, air traffic controllers or ground controllers have to decide by their own experience how much time from this gate to this runway it might usually take. And given that there are 2 aircrafts already, the runway is occupied for the next 20 minutes, let's say. So, and this aircraft would take 18 minutes to arrive. So I might as well ask him to wait at the gate for 2 minutes instead of burning the fuel for 2 minutes on the tarmac, on the taxiway. So a lot of that had to happen in the mind of the controller. And so this basically waiting the aircraft for 2 minutes on the gate is what we call metering. You basically metering, or you're controlling the start time of this aircraft, or in other words, the fuel burn time of the aircraft. So that when it really starts, it does not find any problem, yet the runway is not stopped. So those was the pioneering ideas of a virtual queue, that the aircraft still queue, but not physically, but virtually. And then you tell them then this is the right time to go, and they move. Even before that, when we had very less traffic, where we didn't have, basically the resources were enough. The capacities were more than the demands. When this was the situation, then it didn't really matter. You can ask the guy to leave the gate, and reach the runway when they were ready. That used to happen when we were not really bothered about the fuel, the environmental aspect of aviation, or for example. So back then everything was enough supply. But later, as traffic has grown over the years, and the prediction are that in the next, by 2037, there were predictions that we would double the amount of traffic that we have today. Let us sink in. From 1800s to this time, the amount of traffic that has come into existence will just double. By 100% will increase. So if we were to operate with those protocols that existed back then, we would end up in a very bad situation wherein a lot of delays, a lot of misconnections we would see every day. So we need to come up quickly with algorithms which are efficient and with actually make use of data that we already have, instead of just relying on human intuition and human experience. But that is good, but then it takes a lot of time for humans to develop their intuition, and quite honestly, they're not always optimal. So a lot of work that I've done is basically using deep reinforcement learning to control the start times. So I would make a simulator. I would simulate airport operations and basically task a deep reinforcement learning agent to control this traffic. And this agent, over millions of iterations, would learn how to basically find the sweet spot. So the objective, as I said, the objectives are very clear. We want maximum runway utilization and we want minimum delays. So the better the agent is able to do over each scenario, the more we reward it. If it ends up doing bad, we penalize it, to train it to recommend advisories to controllers that can maximize the objective. So again, it's a very interdisciplinary field. We borrow ideas from different areas. My line of research was, this is a very big topic, departure metering, but I did departure metering, but using a specific methodology, which is what we call deep reinforcement learning. And it turns out that it works quite well.
That's very interesting. So before we kind of dive into your specific model or your agent, what is the common way to do this in a country, like other countries that see a lot of traffic, but maybe they don't have access to this kind of research? Like any of the big countries, like how do they do things that are inefficient in this particular area?
Right. As I said, the research in this area started in 1980s, almost 3 decades ago. I think the first few papers came in 1987, 1990, which really talked about that you need to do something about the congestion on the air side. But different researchers, of course, have their own methodologies. A lot of work in the last decade, especially, has happened using queuing theory. They have models again. Queuing theory is, for those of you who don't know, queuing theory is again theory basically that you picture or you model the airport world as different queues that are at different locations on the airport. Again, this queuing theory has been very well studied in areas like McDonald's. You have queues of customers waiting for their orders and some customers waiting to give their orders. In banks, you have customers waiting. Back then in the day, you would queue for your turn at the bank counter, and then you would go and get the services. So these problems have been very well studied about queuing theory, that how you minimize the queue size. So a lot of that research happens. But to be honest, to answer your specific question, what airports around the world use, that's something. So for the most part, there is no algorithm, as I said. For airports which are in let's say not so rich countries, they would the controllers would go by their intuition. In countries where there are algorithms, they don't make it. I mean, those are algorithms which they don't disclose.
I see.
Yeah, but we know that, for example, a lot of this research has happened in US, in MIT. They have their airports. They partner with airports, like we do with Changi. So they partner with airports, and we know that they have applied those algorithms because those reports have come out. But what really goes inside their software? So every controller has a display on which he sees a radar display, and through the window he can see the live traffic. There are some advisories. We have this Advanced Surface Movement Guidance and Control System. We call it ASMGCS. There's a system that basically gives you all these recommendations. Basically, what route you should assign the aircraft, what time you should assign the aircraft. So there are these systems. For the most part, it's basically extrapolation. So you know a certain state at a certain time, and you extrapolate that given that these instructions would be given, how the future scenario would look like, and then work backwards. So if I know that in that scenario 20 minutes of queuing time will be incurred, so I go back and I ask this aircraft to wait for 20 minutes because you'll just be burning the fuel for next 20 minutes. So a lot of that is simple extrapolation. But the problem occurs when our models of the world don't work, or our plans don't work as they were scheduled. Because inherently airport is a very uncertain environment. And there could be 1,000 sources of uncertainties. Weather could be one of it. Aircraft breakdowns could be one of it. A late passenger could be one of it. There are so many variables that if you model a world, what I mean by modeling is basically writing some mathematical equations that would hopefully abstract out the reality. But reality always is more complex than any mathematical model can explain. We have so many other sources. So the approach that we took was, we said we would not model the airport environment. So we would simulate the operations, and we would have different sources of uncertainties. And so the idea is that if the environment is realistic enough, can the agent in this uncertainty perform good? Can it manage those two metrics? And if it can, then by the logical extension, it can do well in reality also. So we work with this premise that we will create an uncertain environment. We'll not model it in an equation, but we'll just simulate everything, every source of uncertainty that we can put in. And then we would expose this agent to this uncertain environment. One thing that machine learning, and specifically not just deep reinforcement learning, but almost every machine learning algorithm is good at, is basically abstracting out the uncertainty that exists in the environment. So we thought of kind of capitalizing on this capability of an agent that learns through trial and error. If there are millions of scenarios, it has seen enough scenarios that what one decision essentially led to. And so try to work out a policy. We call it policy. Policy is basically, given a certain scenario, what action should the controller take? The idea was to come with these efficient policies.
When you say you're not modeling the real environment, not using equation, then how are you building this virtual?
So there are certain. So for example, as I said, we have Newtonian motion for the motion of the aircraft. So we of course use those equations to model the movement of the aircraft. But there could be different sources of pushback delays, right? And then could be, and then we could learn these delays from the data. You could see the data, and you could see statistically.
So this data is coming from a real airport?
Yes.
Okay.
So then you can take the real statistics of the operations at the airport, and then add all those sources of uncertainty. The uncertainty in aircraft landing times, the uncertainty in aircraft pushback time, the uncertainties in aircraft taxiing time, the uncertainties in the routes that the aircraft would eventually take, right? And the uncertainty of aircraft speeds. So all these are so much uncertain, but we can look in the data that historically this was what we saw. So if that history is any indicator of reality, and if you can play out that reality and the agent can still do better or good in those situations, then you can do away with a lot of modeling or abstraction, as I put it.
So are you comparing with also actual delay times and
So we would compare as I said, this work at this moment is in the realm of simulations. So we compare the metering policies with non-metering scenarios. So non-metering scenario basically mean that when it was a scheduled start time, the aircraft would start at that time without any intervention. So for the first set of results, we compared our work with with basically no metering. But then a later part, we compared with the algorithms that was already out in the open domain, and which were also simulation based. You can't compare apples with oranges, right? Because there are different sets of assumptions, there are different data sources. So there were some algorithms that were already there, which were trying to do this stochastic optimization in the realm of probabilistic events. And then we used our method and basically benchmarked the performance of our method with their method. And then within reinforcement learning also, there are many algorithms. I'm talking about the algorithm that figures out how to find a policy. Like how do you intelligently move towards the global optimum or the optimum? So then we had different sets of experiments in which we tried different algorithms and tried to find out an algorithm that was stable enough and that would consistently outperform other algorithms. So the comparison essentially, the benchmarking essentially is against no intervention, as in no metering. And then you have metering and you use the state-of-the-art algorithms.
But you have two objectives, right? One is about the utilization of the runway, and the other one is about the time, right? So, and they sort of seem contradicting, right? I can increase the utilization of the runway, but then I'll get more delay.
Yeah.
I can reduce the delay, but I'm not utilizing. So how do you compare different algorithms when you have two contradicting objectives?
Yeah, absolutely. So for the method of, when I was training the algorithm, it would be just a linear combination of both of them. So you have basically equal weights to both the objectives, and you can always tune the weights. So what I mean by weights is you have a reward function. In reinforcement learning, you have to define a reward function. Basically, how much reward would be given to the agent. So we have a reward function that is a combination of the runway throughput, or runway throughput basically mean how many aircraft were serviced in 1 hour, and you have a delay, taxi out delays. So how much? So what I mean by delay is that if the aircraft were to go from start to the runway without stopping, unimpeded, how much time would it take? And actually, how much time did it take? You subtract them, the difference, the delta, tells you the delay. So the idea is to minimize the delta or the delay, at the same time keep the runway pressure consistently high. So here's the thing. In non-metering scenarios, as we are discussing about the trade-off, right? This is always a trade-off, and there are two competing objectives. In the non-metering scenarios, you would not stop the aircraft. You would let it go. And as I said earlier, you would have long queues. So you would have a lot of good runway utilization. The runway would never be staffed, but then you would have long delays, a lot of fuel burn. The other extreme is you just kill the competition. How do you kill that? You only release this aircraft when there is no traffic. So in this case, the aircraft goes and does not encounter anything, goes unimpeded, fly off, take off. What happens in this process is the runway is starved, because in the time it goes, there's no runway utilization. So you want to find a sweet spot. Our work showed that you can significantly reduce the delays. Now we do a lot of experiments with basically artificially increasing the traffic also. Like we would make it 50% more than the current one. And so the current traffic usually at Changi Airport is like 30 to 40 aircraft serviced at one runway per hour. So we could move it to 70. Which is sure going to give you some delays. The runway would always be in use, but you would have some delays. You want to serve those aircraft. So we checked the performance of the algorithm from in simulations. You can do whatever you want, like you can put 10 aircraft only and you can put 70 aircraft, and then you kind of see how the algorithm performs in all these scenarios. So now the competing objectives of runway throughput and taxi out delays, we basically combine them as a single reward function. But then now to answer your specific question, how would we evaluate the performance? So we have the scenario, we have recorded performance of all the algorithms. Now we can go back and see how much was the runway throughput for that scenario by this algorithm and by this algorithm. And then you can just compare the performance. There's like a post comparison wherein you can really see those hard numbers, operationally important for airport, for air traffic controllers, for air navigation service providers, and then just compare them. But then while training, it was kept relatively simple, and then this research, a lot of iterations are involved. So you think that keeping a certain reward would give you the desired output, but then you can always change the weights and see different kind of behavior from the agent. So for example, there are a lot of iterations, as I keep saying that. So initially when I started, I thought that it would be a fairly straightforward problem, that I would just have runway utilization as one of the objective or one of the reward component, and I would have delay as one of the reward components. But then I realized that the agents or reinforcement learning, at least unfortunately at the moment, doesn't learn that way. You need to give them a lot of short-term rewards. Basically, so if going back to this earlier definition of reward, if I would give them this reward of a taxi delay or a runway utilization, they would only learn at the end of the scenario when the aircraft has reached the gate. And these algorithms don't learn efficiently that way. These are what we call sparse rewards. We want to guide the training of the algorithm. So you want to give them immediate rewards at every good thing or every bad thing that happens. So that the reward function was designed so that every pushback would lead to a positive reinforcement. Every takeoff would lead to a positive reinforcement. So the central piece or the central idea of basically encouraging less delays was going back to the definition that what causes delays. And then we saw, okay, that the stop and go movement basically is an indication of there's a delay. So then we kind of would reward high velocities, high cumulative velocities on the airport. It might not sound a very very breakthrough idea, but it really changes the whole performance, because now the rewards can be computed at each time step. The velocities can be computed of the airport at each time step, versus a reward that you were going to get only at the end, which was the delta. So if the speeds are okay, the agent is always given a good reinforcement. They're doing good, and then if the runways are being used, you always give it a good. Now it has to balance between keeping the runway pressure, and also we have this, what we call is a later gratification. The gratification about the runway utilization would come at a later time. The positive speeds or the quick velocities would be felt quite quickly, but then the agent has to globally optimize not just the immediate rewards but also the far off rewards. This is quite an active area of research, and a lot of people are working in this domain of how do you design good rewards, how do you design a good state space, how do you design a good algorithm. All these are very hot areas that right now are being worked upon, and there are a lot of moving parts, which basically makes it a fertile ground to research.
Quite fascinating.
That's very fascinating. Like how something as small as just giving it immediate gratification versus like at the end. That's very interesting. Yeah.
But then you still have the issue of generalizing the model to different parts of the world, right? Because
Absolutely.
then the uncertainties are like quite different in a snowy country or a rainy country. So how do you deal with that?
So again, a nice question. So there's an area of research again that is called transfer learning. You learn something in, let's say, in one airport. Can you transfer that learning to another airport? So to answer that conclusively, there have been some attempts at doing that. Like people learn in some part of en route airspace, and then they go to another area, or let's say the same Singapore airspace, but they go to another section of the airspace and then try to see the learnings at one sector. Does it generalize to the other sector also? And the answer at the moment is that not completely. Like when you have trained an agent on one, let's say one airport, it does not necessarily translate to another airport directly. It's not a one-shot learning, because as you said, there are different operation protocols. There are different the configuration of the airports are different. Just structurally, the network is very different. There are more runways. For example, Atlanta has so many runways, crossing runways. The geometry is different. So, and again, the weather is different. The runway usage is also different. Changi Airport has this staggered runways, staggered parallel runways, wherein each runway, it's like one runway is dedicated to departures, another runway is dedicated to arrivals. You don't have any interaction for most part. That makes the job easy. because then you don't have to worry about incoming arrivals. Whereas in other airports, it could be much more complicated. So yes, it does not directly translate, but very surprisingly and happily, we have seen evidence that the trained agent in one sector learns quickly or quicker than if it was completely, if it were started from scratch at a new airport. So the convergence rate of the policy, we say the policy is converged when you are seeing good results consistently. So you change the scenarios, but the agent is still able to do it well, which basically means that it has learned a general policy. So there's a curve, and then it plateaus. You see that yes, now the agent has reached its peak. Now it can generalize. So that peak comes quickly if you use an already trained agent to another airport, because we understand that there are differences, but there are some commonalities as well. So the commonalities, again, this is our attempt to intellectualize this stuff. That there's maybe the agent has abstracted this idea of. Again, this is a very hot area of research about how you can make it general, how you can make it generic, in a broader data science or broader AI or machine learning community as well, and so also the case in airport operations management.
What does the deployment for this kind of network look like? You mentioned that the control tower has like a display in front of them, right? So if you were to deploy your agent, like some version of that agent, what is it telling them? Like, what are you mentioned something about policies, like what do those look like for the actual control tower?
Right now I'm doing exactly that. I made some algorithms. Now I'm creating the front end or the interface for the controller to interact with the algorithms. So how it gets deployed is like this. I'm preparing a display wherein on one side you have the schedule for the day, and on the other side you have the airside map with the live traffic information. The controller can see the traffic and can see the schedule. In the schedule, I show them a recommendation. So you have the schedule which says that this is the scheduled start time of this aircraft. In the same region, I tell them when the time comes, like let's say this aircraft A was to start at 9 a.m. and the time 9 a.m. comes, my algorithm recommends them that either you should push back, it's okay to push back, or it would be better if you hold it. So it's a go, no go sort of recommendation. Don't let it go, let it go. At this point in time, we understand that controllers are not very happy being dictated some things. So what we have done is we just providing it as a recommendation. So the controller still gets to decide what it gets to decide. So the controller can hit a button near the advisory, which can override this advisory. The advisory says stop it, but you can still let it go, or can choose to follow it. So now after we have this interface ready, we will be doing this human in the loop experiments or ADCO validations, wherein we would make a real live controller sit in front of the system and then show them this advisory and do another set of experiments wherein we don't show them an advisory and they are on their own, and basically compare the performance. Not just the performance on these two metrics. I mean, you can always compare the performance on these hard metrics of objective metrics of runway utilization, taxi delays. But over and beyond that, we also want to take into consideration a personalization for the controller themselves, because not every controller is the same. Not just one recipe works for everyone. You need to personalize it. So you need to find in the solution space, you need to find a subset that works for this controller. So basically what you do is then you have another loop of training wherein the recommendation happens, but the controller action or the controller response to those recommendations also play into fact. So for example, when we use YouTube, we are shown some recommendations, but not every time we watch those videos. But then the time that we watch those videos, our clicks are useful for the algorithms that basically makes those new recommendations. So similar to this fact, we would take those actions into our the brain of the algorithm or the policy as I create, and then fine tune it to suit this particular controller. And we can do that for n set of control.
Again, very fascinating. So you're, like that even I think will optimize more, because now you're also, it's just like I said, you're fine tuning to the personality of the controller.
So we have to understand it may be less or maybe suboptimal in this case, because controllers can be you see, algorithms would recommend them what is let's say optimal. But the controllers don't find that, and there's no buy-in. So then for buy-in, we might have to then stick with what controllers like. So again, there's a trade-off. Personalize it, but at the same time keep the recommendations sane. Again, there's a very good area of research wherein how much you optimize and how much you personalize, and to what degree you keep doing that. Again, that's something that I'm consistently thinking about and working towards. But first thing for us is the buy-in. First, if they're ready to work with the system, then we can always tweak it later to make it more optimized. But initially is to basically show them that this tool can really reduce their workload. And so now what they have to do is just supervise or manage the small decisions. They don't have to, because the algorithms are really good at monitoring. You see, there are different things happening at different parts of the airport, and we feed in all that information to the algorithm. Our state space. We didn't get a chance to talk about that, but our state space basically is a lot of things. But one of them is a relative position of each aircraft on the surface. An algorithm can basically abstract all this information at once, but for a controller to focus on all of them is nearly impossible. So we know some algorithms are good at some things, so let's capitalize them. And again, there are another area of very hot research is wherein you don't really need to personalize, but then you design something that complements the controller's strengths. The algorithm has some strengths, but algorithm can be, the recommendations can be very weird sometimes because the algorithms don't have context, whereas humans have context. And as I said, things can be wrong due to multiple reasons. Weather could be one of them. The controller can think about the context, that in this context, will this solution really work? Or should I really think about doing this stuff? So that another paradigm of thought is can you complement each other? The strengths of this, can it complement decision making of this, and can his or her decision making or this context thing can help the algorithm? Yeah, again, a very fascinating area. It's just a very fertile ground for all this kind of thoughts.
Yeah. Actually, you just remind me of something. So, like in chess, it's also deep learning. It's deep learning models, and a lot of times I'm watching like chess analysis online. Like the commentator will say, okay, this is the recommended move by the AI, but it doesn't make any sense. But we know, everyone knows, like no one can beat AI. Like if you play a game against the toughest AI, so it will always win. So we know that, and yet still we say, oh, this recommendation or this suggested move doesn't make sense. So there's always this human kind of ego, I would say, maybe, or maybe, I don't know what to call it, but usually you like to have context always with any decision, right? So I think that's important to consider.
There's again a very nuanced point. So algorithms and these decision-making systems are very sensitive to any changes. Sometimes those changes are not perceivable to us. We cannot perceive them because they're very minute. But these algorithms can view them, can actually sense that because the state space has changed now. And their recommendations could be based on that. Now, a lot of flag that comes because, as you said about the algorithm, this thing called AlphaGo, and there are all these algorithms that have shown that they've outperformed sometimes world experts at those games. Chess movement, for example, at this point in time may not make sense, but looking down the line, probabilistically, if you just extrapolate all the moves that are possible, that might make sense or might confuse the other guy, your opponent. So there could be infinite reasons, but just because that is a black box, there's no explainability to attach to it. Like it does not tell you I'm making this move because this. So a lot of that is not again taken. You really need to figure out what is more important. Is optimization the most important thing, or explainability also? Sometimes we can't really blindly believe in algorithms, like in medical research. We have to take into account explainability because lives are at stake. But then other areas which are less safety critical, less dangerous, you can give them some chance. And to be honest, not every move that the AI algorithm would make would make sense, and even would be bad. But this is how those algorithms learn. You see, over iterations, that what algorithms work. And at the end of the day, I believe that there has to be some explainability. We don't want to go into a world wherein we just blindly believe what we are being told. So there always has to be some explainability. This is another paradigm. Earlier, people used to write algorithms. Algorithms were what? Step-by-step instructions. Let's say if you want to cook something, you want to cook some sweet, you would follow a recipe. Do this, and then you get this sweet. The paradigm change that comes with machine learning and with deep reinforcement learning is that we don't know the recipe ourselves. So we tell them the end goal and we tell them to figure out the recipe themselves. So it works in the backward loop. So the idea is they do some random stuff initially because the policy is just random. Do anything, equal probability of every action. But then through the rewards, they are tuned. The policies, basically neural network policies are set of weights. And you change the weights to to basically reduce the loss. You have a loss function, you want to minimize the loss. And a maximization of the reward is basically giving that reduction of the loss for you. And so the more reward you get, the better those hyperparameters at that point in time, or those actions for that particular state are reinforced in the algorithm. So good actions that bring you more rewards are reinforced. Bad actions that less a lot of penalty basically reduces the likelihood of taking the same actions if you see those future states, similar future states. So yeah, again, that's a very interesting dialogue for a lot of people, that how far can you trust them, and if they don't make sense, there is this thought that they are supreme or they somehow better than us. But those algorithms that we know have outperformed humans are still in a very limited domain, the chessboard. You know all the moves beforehand. Whereas reality is much more nuanced, much more uncertain. An airport, for example, is way more uncertain than a chessboard. Chess, the moves, that a king can only do this, a queen can only do this. They don't have a probability associated with it. The probability is with the opponent's actions, what actions it would take, but not with how things would happen. So the same controller, same aircraft can leave the same gate, but can reach the runway at a different point in time in different scenarios. There's a lot of uncertainty. And a lot of that has to come with the surrounding traffic. Right? At one instant you have a lot of traffic. At one instant you don't have a lot of traffic. But at one instant you have a lot of traffic near the aircraft movement trajectory. In other cases you don't have that. So this brings in a lot of new variability. So you can't really hard code a solution. Even for chess, as per some estimates, there could be billion moves. And so if you were to really do it brute force way, wherein find all the possible answers and then try to find the branch that would give you the optimal, that would take us years to arrive at those decisions. But we want something quickly. We don't have forever. We have traffic to take care. So it should happen quickly. So I mean, it's one thing to perform good on a game of Go or to perform good on a game of chess. It's another thing to do it in real life, wherein you have actors, humans, which are quite often not as predictable as you would want them to be.
Right. So context is very critical in the real world.
Yes.
Whereas like in a game, the context is very limited, and eventually it's conceivable that with enough computing power,
right,
you can achieve the entire context of that.
Right.
So where do you see this field going in the future? Like, the current challenges, like you've solved a few of the challenges before, right? Like people doing it themselves or not using algorithms and so on. And then you solve some of them. But what are the challenges you face now that some new research is trying to fill in?
I think the challenge lies in, first of all, there's a real challenge of catering to the increasing traffic. We know that traffic would increase, and the methods that worked in the past will no longer be enough or sufficient to help us manage the increased traffic. Now, as Changi Airport did, you could increase the infrastructure. You can make a larger airport, but that's not possible everywhere and all the times. There are so many considerations, so many constraints when you're operating as an airport. For example, in the US, flights cannot land after a certain time. In Europe also, because that noise that the aircraft create bothers the people around. And then sometimes there are environmental reasons. You can't just make things. You need to cater for the environment. So increasing the physical infrastructure is not it's not an intelligent solution. You can do that, but it involves a lot of money. And then it also has all these problems of environmental regulation problems as well. So then the question is that given what you have, you need to manage the demand intelligently. So now the question is, can humans do that? And we know that we have a certain cognitive limit beyond which we can't or it would tax us a lot. You can just put in more people also, but there's a limit to that as well. Another question is, how can we make the lives of controllers, the people who control this traffic, easy? So I believe the future directions is basically using these algorithms to aid the decision making under uncertainty for the controllers. And then of course there has to be a buy-in. So a lot of future research, I believe, would be about how do you develop trust between these socio-economic systems. How do you develop a system wherein controllers rely on these advisories and can fall back upon them? And how do you design algorithms that are robust and also explainable? Because if a controller knows why you do something, the chances of a buy-in are much higher. Because I can have, even though the answer might be wrong, but I need to start giving you some solutions that are explainable. So a lot of this research, I believe, would go into that direction, wherein you would need controller buy-in. And like aviation, it's a very safety critical system. So there are a lot of regulations in place. You can't just put any system that you want to out in open and operate the environment. You need regulatory agencies to certify those. And right now, it's a big challenge to certify machine learned black box models. So a lot of research is also going in that direction. Then how do you, again, it basically ties back to trust and it ties back to explainability. So I believe that a lot of in future this area, since we know that we have to manage the demand, the task is at hand is challenging, and we know that we have some algorithms, we have some tools that can make the lives easier. And so if we can give controllers more, basically if we come to the situation wherein controllers are managing the traffic instead of taking each decision, and they are like more like supervisors, and they are, instead of supervising different humans, they're supervising algorithms or different tools taking decisions. It would be inevitable if we have to go ahead in time. And for countries for which airport operations are critical to their existence, countries that rely on tourism, countries that rely on travel, and there are many countries like those. So for them, it is of strategic importance for them to basically develop and just put these tools in the workflow.
One last question. Do you see a time where control towers are only run by computers?
Maybe in the far future, yes. But those questions are very similar to, do you see a time wherein there are only autonomous cars, there's no human driver? These questions are very similar to, do you see a time when there are no pilots? At least at this moment, I believe that is not the case. Because for safety critical systems, you need to have humans. At the moment, what we are doing is just delegating some of the routine work to the algorithms. But the critical thinking works that requires some context, that requires high order thinking skills, are still done by controllers, human controllers. But you never say never. You don't know if eventually that would happen. But not likely so much in the air transportation domain, at least as I can see. If you would know that a lot of algorithms that work behind the traffic signals that we walk on the road, they are algorithms actually. Now it's not just a fixed cycle. Earlier it used to be a fixed cycle, like 20 seconds yellow, 20 seconds green, 20 seconds red. Now there's no more the case. Now it basically, if you have seen in Singapore, there are sensors on the road.
Yeah.
So when a car goes, so there's an indication for them that how much traffic is basically waiting in one direction. So there's more traffic here, then they reduce the time for the red signal and they let it go. So I believe every technology has to go through these cycles. When first thing is the buy-in. So you need to reduce the threshold for the buy-in, and then you continuously improve it so much so that when humans become comfortable with algorithms, let's say controlling the traffic lights, but that has come after a long series of iteration and a long series of research and a lot of experience. I'm very sure those traffic lights may have led to very difficult situations, sometimes problematic encounters.
Yeah, that happens when they're all off suddenly.
Yeah.
It's a mess.
So and then there are various different questions around this also, that what happens, that controllers ask us that will our jobs be taken? All these things have repercussions. I do acknowledge that. But as one of my as my supervisors put it the other day, that that jobs are not lost. It just leads to evolution of jobs. So for example, with ATM, with the machine that we take money from, it replaced a certain profession of people basically sitting in the banks and giving money. It replaced them, yes. But then those people then had to do another set of jobs that required a higher order thinking than just giving out the money and counting it. The machines could take care of it. So I believe it would not be a complete... I don't see in the near future that controllers will not be there in the control tower. I believe that the responsibilities that they now have would then be changed or would then evolve to suit that particular point in time, and it should be incommensurate with what the task we have at hand, and which is basically a lot more traffic to handle. So you can't really focus on each thing, but you need to focus on the critical areas.
I mean, the examples you give are very relevant and like applicable to what research you're doing. Like, it's very easy to understand. So I appreciate that. I think we can end up round this interview off with how you spent your time during the PhD. Like, if you're not doing research, what do you find yourself doing?
Yeah, most of the time was actually spent in research labs. So what I would do otherwise, I would travel, and I would read travelogues and sometimes some novels to take my mind off what I was doing. Yeah, I would spend a lot of time in masajids also. That kinds of gives me some sense of higher purpose than the everyday research that I'm doing. And truth be told, there are days where you're not getting results or you're not getting anywhere. Things are not working. So you really need those moments where you actually can reflect back on your lives and think about, when we are doing research, we are really we get pushed in the corner, and we are really siloed. That a failure in getting results basically tell us that we are failure in lives. But then it basically, anything that gives me some space to think about that life is more than research helps me come back the next day or the next week or the following month to the same problems with a clearer mind. Sometimes you're just stuck, banging against the wall, and then you need to some time off. You need to go back. And for me, religion always does that. It gives me a sense of calm and peace and a sense of higher purpose than just the mundane day-to-day activities. And so when I go back, I'm with a clearer mind, and sometimes most of the times these breaks work. So that is how I would just not do research and take a break.
Beautifully put. Thank you so much for joining us today, Hasnain.
Thanks a lot.
And
it was a pleasure.
We'll see everyone next time.
All right. Thanks a lot.
Thank you. Bye-bye.
Bye-bye.
Bye.